My talk is about using AI for data enrichment, because everyone is talking about AI and how AI is solving all the fancy problems, but actually nobody is really talking about the data foundation, and that's why I wanted to showcase you a project we're currently working on. So a little bit about myself, a picture of me when I was young. I'm working currently as a senior data engineer at E.ON. As Marina said, we are over 170 people working on different data and AI topics. Before, I used to work in consulting at BCG, and from my background, I used to study data science before AI was fancy, and I also have a bachelor degree in international business studies. So touching a little bit on our operations at E.ON, every time I ask my friends or my family, what do you know about E.ON? They're always like, they send us a bill for the electricity. But actually, we have 3 pillars in our business. And the 3 pillars are energy networks, energy infrastructure, and energy retail. So most of our money is generated by operating the electricity and the gas grid. And it's actually the backbone of AI, because we are using so much electricity, and therefore we also have to invest a lot of money into the infrastructure, into the electricity grid. The second pillar of our business operations is energy infrastructure solutions. So say, for instance, you're a big consumer of energy, then you would also need to have some proprietary project, and there we can support you with some custom solutions. And the third pillar, that's basically the pillar which is most famous, like where most people know our business operations, is energy retail. So actually the sales of energy. So last year I was working in the asset management. As I said, we're operating the electricity and the gas grid. And to do so, we have a vast amount of assets that we need to operate, but also manage. And there we were working on a data quality project where we used machine learning to enhance the data and also to improve the data quality. So as I said, everyone is talking about AI. I have the feeling every week we have new algorithms. Somehow it cures cancer. You have apparently quicker customer complaint resolution. You can complete your code quicker with AI, and apparently there's also impressive productivity gains. But if you look under the hood, what no one is really telling you, if you don't really have the data foundation, you cannot really apply AI, in my opinion. So that's why I'm saying real impact can only be unlocked if you have actually good data quality. And that was what we were focusing on, because what you will see in all the marketing slides is basically you have your data, then you're throwing AI on it, and then you will have in the end the solution for everything. I feel like you're hearing it everywhere, especially from the US and China. But actually, if you really look into enterprise applications, the reality unfortunately looks a little bit more like this. You have garbage data, you have different systems, you have legacy systems. It's not really interconnected, and you're throwing an AI on it. And what happens? Obviously, the output is most likely also garbage, because you cannot really produce anything good out of garbage, right? Because you cannot really create diamonds out of garbage. And what kind of garbage? Good question. We can have a discussion on it later. So when we looked at our asset data, we found out that we have basically a new system where we are managing our assets, but we saw that basically the asset data was quite incomplete. We had a very, very high share of missing data. There are various reasons why this is the case. So if you look into all the assets that you would need for the electricity infrastructure, the life cycle is actually quite long. A transformer can be used for several decades. And back then, you actually didn't really need the data. So back then, we also didn't record the data. Also, we have different business models within E.ON. So everyone's a little bit different. And we're right now also in the state of standardizing and also having a uniform data model. And ultimately, also in this space, we're operating the critical infrastructure. The regulatory requirements are actually increasing from the European and also from the German side. So that's why we need more data, and especially we need more good quality data. That's why we were thinking about using machine learning, or you can also call it AI, to actually automatically fill all the blind spots of our data. So what does it mean? Let's just have a look at mid-voltage. So to operate the energy grid, the electricity grid, on the mid-voltage level, we have 76 distinct object types. If you look at how you can describe these objects, we have in total 762 different fields. And if we just have a look at the different objects, like the electricity station, the local network transformer or switch blocks, you can see we have a magnitude of objects. Just for the electricity stations, we have 150,000 stations, like physical stations. And we have like 26 descriptive columns for this electricity station. But we have quite a lot of blind spots due to the reasons I mentioned earlier. And it's just impossible to have a human have a look at all the different data fields and fill them up manually. One idea would have been to say, okay, the clerk that is going to the electricity station during the maintenance cycle should just have a look at the information and just fill it up. But imagine with 150,000 electricity stations, how long does it take? And you can imagine the clerk is also not the fondest person of doing data quality checks. So that's why we tried out using a machine learning approach to fill up these blind spots. So actually it was quite a nice model machine learning project. So the different steps that we took were first having the data cleansing, then we looked at outliers, then we looked at correlation and also clusterings, then we taught several machine learning models, and in the end we applied a model and also validated it with the business. And for each step, there's also some detailed slides that I will show you what it means and what we did in each step. And in the end, we got basically a recommendation for each object and each particular field. So that was basically our approach. If we looked at the data cleansing, that meant we did classical transformation of data types. For outliers, we looked into the field data. Is the quality good? And if it isn't, we also did some corrections. And we also basically did some business logic in the outlier detection. For correlation, we looked at fields that were highly correlated, because these are normally good fields where you could just then basically take the information to fill up everything that is missing. So say, for instance, weight and height, they are normally positively correlated. So if you don't know the weight, you probably can infer it a little bit with the height. So that was basically our thought here. And then looking at the model step, we were looking at different models, tried them out, but most of our performance improvement came basically from the data cleansing and the correlation beforehand. And in the end, we had several approaches that we then validated with the business. But let's have a deep dive on each step. Looking at data cleansing, you can see for the transformer, just as an example, what kind of different information we were having in our SAP database. You can see we have stuff like weight, we have usage type or whatsoever. But in the data itself, we also saw that there was quite a lot of irregularities. So that was for us, first of all, super important to understand how's the distribution and is there something we need to correct beforehand, because garbage in is garbage out, basically, right? So here you can already see that there's a lot of variance within the data. Then next, when we looked at correlations, we basically just looked at a classical correlation matrix, and the higher the correlation, or also on the negative side, if it's very negatively correlated, the more you could say you could just limit your data set to the variables that are actually important to predict everything that is missing. And then it was actually quite nice if you look at the chart that there were some fields that were automatically detected as being very highly correlated for each other. So that was also quite cool for us that we could also see it in the data that from an electrical engineering point of view, these fields are actually positively correlated. And then looking at the actual algorithm, we still use a mix of rule-based and also machine learning, because in the end, we are operating the critical infrastructure. And if you can fill up everything with rules, why not, right? Everyone's talking about AI, but if you have hard-coded rules and they're working, you should definitely always go with the hard-coded rules. And that's why when I have the example with the transformer, we checked for each object, can we apply the rules? And if so, we give priority for the rules over the machine learning algorithm. So we had two sets of rules. First of all, we had the business rules. So say one column is like this, then column B behaves like that. The second set of rules was basically from the hierarchy. So in the mid-voltage area, you have the transformer. You can find it in the station. And in the station, sometimes you find some information that is missing on your transformer side. And then next, what we used were two sets of different input features that we tried out. So first of all, we had the clustered variables, which were basically the variables that we saw from the previous slide that are highly correlated and which are the input features for our clustering model. And then next, we also had a baseline model, so-called baseline model, which basically existed with a fixed set of variables that are mostly important for predicting everything that is missing. And then we basically did a very classical approach. We had a validation set. So for each variable that we wanted to impute, so to fill up, we set aside 10% for validation. And we had also different metrics to test it out. And in the end, we also had these really empty data where we had a step to validate it with the business. But I will go over that later on. So we had two sets of variables. So we had numerical and categorical variables. And for the 10% set aside data set for each variable, we basically use the F1 measure for all the categorical variables. And for all the numerical variables, we used mean absolute error. And for mean absolute error, the lower it is, the better your result. And for the accuracy, the higher the F1 measure, the higher your F1 measure, the better your result. Then basically that was how it looked like. So we were quite happy about the result. You can see for the numerical variable on top, on the left side, the baseline result, we did also some outlier correction. And in the end, you can basically see everything that is imputed. And you can see nicely that it's basically the distribution from that particular variable. Also from the categorical side, it also looked quite similar. And when we were happy with the result, we basically sent the result to the business and validated it with them with some, basically representative samples. And then they said yes or no. And it actually had quite a big impact because overall, as you saw earlier, we have just a magnitude of technical objects. So it's impossible to check them manually. Maybe last point about the infrastructure. For us as an enterprise, obviously it is important that we don't have a Jupyter notebook that is just applicable once. So our infrastructure basically looked like that. Everything that was relevant for this use case was basically our SAP asset database. And on top, we were building our infrastructure on Azure. Our computations and all our models were deducted in Databricks. We did the code management in GitLab. And then basically we had proprietary databases for each kind of business and each object in Databricks. And then we, in the end, use a Power BI dashboard to showcase our results. Yeah. Thank you.